Welcome to the second in this series on smart gardens and the role of digital technologies in food and fibre production. In the first video, we looked at how junior school students could build their own water management system. These students at Walhallow Primary School in the northwest of New South Wales built a smart garden that measured the moisture level in the soil and then turned on a little pump when the moisture level fell below a certain level. They started with the system described in that earlier video using code from an algorithm describing the steps that the computer should take. So do this forever. Get the reading on pin 0 of the microbit and see if it's less than 700. If it is, turn on a small pump, and if it isn't, turn the pump off. The improved solution in this video was developed over a year. It took a while, not only because the fully automated system was more complex, but also because we wanted to deal with some of the complications that can crop up in a garden and iterate or build a better version of this system. One such complication was the development of mould, which is encouraged by hot and humid conditions. So we don't want to water the plants in the evening. We don't want to water them during the day either, because the water will just evaporate, but we don't want to water them in the evening because the air is quite humid then. The day's been hot, you're putting a lot of water into the air, and that encourages the growth of mould. So we decided we'd need to put in some sort of timing so that we only water the plants after the heat of the evening had decreased. The other thing that we looked at was how long do I actually need to water the plants for? And we don't want to do that for longer than we need to because it's wasting water and we may in fact flood the plants and cause them to die. So how long is the best watering time? The roots need the water, we decided, so where are the roots? Are they adventitious or tap roots? And that of course depends upon the crop. How long does water take to percolate through the soil to those roots? An experiment showed that with a low flow rate and the soil type that we had and the vegetables that we were growing, 1 hour would be sufficient for the water to reach that level. We had to rethink our original algorithm. We later modified this algorithm from what you see on the screen to turn the tap on if the reading with pin 0 was less than 700. Not 500 as it is in this whiteboard shot. Now figuring out stuff is messy, but whiteboards and goofing around and drawing arrows and perhapsing about allows for rapid changes in our thinking and in the proposed solutions as more and more things are considered. Here's a more formal way of representing our ideas, moving from plain English to pseudocode to code. And you can see that as we go through here, this is the sort of thing that we want to do. We want the water checker to run all the time. So the pseudocode is do this forever. If the soil's dry and it's dark, so in other words, at the end of the day, then if the pin 0 is less than 700 and the light level is less than 100, because a microbit has a built-in light level, then we'll wait for 4 hours for the heat of the evening or the heat of the day to dissipate, and that turns into whatever that number is in milliseconds. Some nice maths in that. Then we water the garden. In other words, turn on pin 2, which then turns on our pump or whatever we choose to use. In this instance, we chose an electric tap or solenoid, as you'll see. Now we water for an hour and then see how things are then. So if our calculations are right and the water has gotten to the level where the moisture sensor is, then we don't need to do anything else. But if something weird has happened, maybe lower pressure than normal in the watering system or whatever, we can allow this to repeat itself if we need to. So we're going to wait for that many milliseconds, which is an hour, and then otherwise we're going to turn the tap off. Now note that the loop will run through one more time. If the soil is still dry and it's dark and the water hasn't reached there, then it will leave the pump on and it'll run it for another hour. So this is what the code looked like. And I've commented this code using the commenting feature of MakeCode to show what each bit does, and you'll see that it's pretty much the same as the plain English, sort of a mixture of plain English and pseudocode in the comments there. So if the analog read pin on P0 was 400, I think this is an experimental one that one of the students was doing, and the light level is less than 100, which they determined was dark, then you wait for a while. That's to wait for the heat of the day to dissipate. And then we turn pin P2, which is connected to a pump or a solenoid, on. We wait for an hour, and that loop will run back again. Otherwise, we'll turn the pump off. So this is the whole thing, the whole system described as an input, process and output system. So the soil moisture probe measures the water content of the soil. The microbit code works out if the soil moisture is below a certain cutoff point, and if it is, then it sends a signal to turn on, in this case, an electric tap. Now, we know that from the previous video, we saw that the microbit can't handle switching a high current or a high voltage device. We discussed that the microbit needs a relay to handle the higher voltage and current that's needed by the solenoid actuator. Now, things that do stuff in physical computing are called actuators, like solenoids and motors. Things that sense things are called sensors. Pretty straightforward. Now, this turns out to be a little bit more complex when we start to get into production. That's how the input, the process and the output works, but of course we need something to power all this. So we want it to run unattended, so we need a solar cell that's going to power everything. We're going to use a small battery, which we got from a battery shop. It was no good for the motorcycle it came out of, but it was fine for what we wanted to do. Didn't have to start motors or anything. And the solar controller will charge the battery and deliver power to the tap. So the battery we got for nothing, the solar controller and the solar cell was about $10, $12 on eBay. And the way these things are all hooked together is like this. The solar cell puts its power into the controller, which decides whether or not it's going to need to put any power into the battery if the battery is not full, and then the battery is connected back through that solar controller, which switches on the power so that the relay can turn the output on. And the output in this instance is a thing called a solenoid, which is a 12-volt electric tap. Apply 12 volts, the tap opens, take the 12 volts away, the tap closes. They cost around $10, $12 likewise on eBay, but you'll probably need to get a plumber to install them for you. So the whole system is now fully automated, doesn't need anyone to look at it. And the battery is being charged by that controller for a cheap solar panel, and the controller is supplying power to the microbit and also to the relay, so that the relay can turn the pump on. All of the circuitry, with the exception of the solar panel, which is on the roof, is contained in a $20 fishing box to protect it from the weather. The red and black wires are connected to the solenoid, you'll see on the left there, and the white cabling connects to the solar cell on the roof. Now, the fishing box has got holes drilled into it in the centre to allow the microbit's LEDs to sense the light level. And the holes are covered by clear plastic to keep everything dry inside. And finally, a padlock deters opportunistic or curious fiddlers. But what if our system breaks down? We need some way of getting an early warning as to whether our settings are right or whether we've made any miscalculations in our algorithm. So, as well as observing plants to help us get the settings right, we planted basil, which wilts very quickly and recovers very well after wilting around the garden edge. So if our system fails, we get an early warning from the basil, which gets very droopy when it doesn't have enough water. We also built 2 bits of checking code into it. So opening the fishing box and pressing button A would turn the sprinkler on for 5 minutes to show that the outputs were working, and we could easily see if any sprinkler head had become blocked, as they frequently do. Pressing button B would show the current moisture reading for 2 seconds before turning the LEDs off. This way we could check that the inputs were what we expected them to be. Now this sort of system can be built for a variety of age groups, from the simple in video 1 to the more complex here. You can pause the video here to see the range of content descriptors that could be taught at different age groups using a smart garden, and these content descriptors are for digital technologies. The smart garden can also be a really good integrated unit, here showing the content descriptors for design and technologies. Again, pause the video to see what options are available. But wait, there's more. Science is also a great companion here, showing opportunities in 3.4, 5.6 and 7.8, as do the others. There's a great opportunity here for the students in 5.6, for argument's sake, to be able to do most of the heavy lifting on this, and the younger years, 3.4, to be instructed by those 5 and 6 kids to satisfy that content description. If you're in a K-12 school, then obviously that benefit or opportunity extends to 7 and 8. So in Smart Gardens 3, we'll look at how the concepts developed in the school smart garden might be applied to a larger scale, commercial food and fibre production.